In the systematic or IUPAC names of organic compounds that we've seen so far, there's no three-dimensional information. The name is generated entirely from the connectivity of the molecule, right? Basically, parent chain and substituents, and where the substituents are located in a connectivity sense is the only information we need to generate the name. This is not a fully exhaustive system because it does not allow us to distinguish between stereoisomers. For example, here on the slide, we have a pair of enantiomers, and we can tell they're enantiomers because we have one tetrahedral stereocenter with a difference in configuration, an implied wedged H here, and the Cl change places to generate this structure with the Cl on a wedge and the implied H on a dash. So these are enantiomers, but they have the same systematic or IUPAC name, right? They are both ethyl 1-chloropropyl ether, based on the fact that we have a propyl group here, a chlorine substituent at carbon 1 of that propyl group, and an ethyl group here. The same is true in the other structure. Chlorine group at carbon 1, 3-carbon fragment, and a 2-carbon alkyl group over here. So there's something missing from our nomenclature system, right? The nomenclature system doesn't account for stereochemical differences. And so we need to add on a new naming convention to account for stereochemical differences. And that's going to be the R and S labels at tetrahedral stereocenters, and more generally the so-called Cahn-Ingold-Prelog system for assigning what we'll call configurational labels. You can basically just think of them as names to particular configurations, the way groups are arranged around a tetrahedral stereocenter. And as we'll see, and as you'll be able to do yourself by the end of this video, this compound on the left is S, ethyl 1-chloropropyl ether, with the S configuration at its lone stereocenter, and the enantiomer is then necessarily R, ethyl 1-chloropropyl ether, with the R configuration at this tetrahedral stereocenter. So these labels S and R now do allow us to distinguish between these stereochemically different compounds, these stereoisomers. So how exactly does this Cahn-Ingold-Prelog system, or RS naming convention, work? Well, essentially what we want to do in broad brushstrokes is, first of all, eliminate the complexity around the tetrahedral stereocenter by assigning a priority number to each group attached to the stereocenter, 1, 2, 3, or 4. Then we're just going to think about that arrangement of groups 1, 2, 3, and 4 around the tetrahedral stereocenter, rotate it into a standard orientation, and then look at the sense of rotation of the remaining groups after that sort of standard rotation. More specifically, in the first step, we're going to assign a priority number, 1, 2, 3, or 4, to each group, and that's based on its atomic number and atomic mass. So the highest priority group gets the number 1, and this is the heaviest atom or group. The priority 4 group is the lightest, if we're just talking about, and we're looking at that atom that is directly connected to the stereocenter. So H being the lightest gets priority 4, Cl being the heaviest gets priority 1, oxygen is lighter than chlorine but heavier than carbon, and so oxygen gets priority 2, and the carbon priority 3. For ties, we're going to deal with ties on the next slide. For example, if you have, and this is very common, 2 carbons connected to the stereocenter, how do we prioritize those carbons? Essentially, we keep looking out beyond that first atom that's connected to the stereocenter, and we'll see what that looks like on the next slide. Once we've got those priorities down, now we can actually remove the specific groups and just look at this picture where we've replaced all of the bonds and atoms with 1, 2, 3, and 4. The nice thing about this is now we've completely abstracted from the original molecule to a general case that's going to be applicable to a wide variety of circumstances. What we need to do now is rotate this sort of standard structure into a standard orientation, a well-defined orientation that is part of the convention that makes sure that when I assign a configuration and you assign a configuration, we're looking at the stereocenter from the same angle. And the standard here is to rotate the molecules so that the priority group 4, the lowest priority group, is pointed back. And so we can think about this rotation as being something like this, in this case, moving this wedged group back to where 1 is, and moving 1 out here, and moving 2 over here, and 3 over there. There's also a sort of trick to doing this involving exchanging 2 groups twice, and we'll look at that on slide 11 briefly, but I think it's a good habit to try to get into the habit of actually mentally or using a physical model, like a model kit, actually rotating around things. So for example, here, the standard view we've got might look something like this, with this white ball being the priority 4 group. What we need to do is rotate this around so that that priority 4 group is in the back, almost like a Newman projection kind of view, right? With the priority 4 group in the back almost so that we can't see it. And then what we're going to do is look at the sense of rotation of the remaining groups. So you'll see that in this orientation, the 3 remaining groups sort of form a triangle. And we're going to look from 1 to 2 to 3 and look at the sense of rotation as our eye moves from 1 to 2 to 3. A clockwise sense of rotation indicates the R configuration, and a counterclockwise sense of rotation indicates the S configuration. So we can see here, for instance, that in this structure, we go from 1 to 2 to 3, and that is clockwise. This is an R configuration. Notice, though, that if we switch things around, if we switch the positions of groups 2 and 3, well, that's the opposite configuration, as we say, and now the sense of rotation is counterclockwise, and that stereocenter gets the S label. So this is the RS convention, and again, the overall idea is we assign priority numbers, we remove the specific groups, just thinking about a general structure, something like this, and rotate it into a standard orientation with that priority 4 group in the back. On a dash is one way you can think about this, or even in a Newman projection with the carbon 4 bond, looking down the carbon 4 bond, kind of this way, is another equally valid way to think about this. And we look at the sense of rotation from priority 1 to 2 to 3. If it's clockwise, we've got an R stereocenter. If it's counterclockwise, we've got an S stereocenter. Now, a few more details about prioritization and rotating. First, prioritization when atoms are identical. So this is a very common situation where, for instance, we're going to run into 2 carbons, which obviously have the same atomic mass. And so how do we distinguish or prioritize these groups? The way we do this is iteratively looking for, and this is actually a key term here, the first point of difference. The first point of difference as we walk along the chains of the 2 groups that we're interested in looking at. And at that first point of difference, the heavier atom is associated with the higher priority group. So here, for example, we'd have no problem identifying the OH group as priority 1 and the hydrogen as priority 4. O being the heaviest atom and H being the lightest, directly connected to this stereocenter. But the 2 groups highlighted in green are both CH2s. So we need to keep moving along. And we need to move to the next carbon along each chain. The left-hand carbon here has an implied hydrogen attached to it. I'm going to draw that in. And the next carbon on the other side has 2 implied hydrogens. And so now when we look at this carbon versus this carbon to prioritize, here they're highlighted in green in this other image, we see that there are 2 carbons connected to that left-hand chain carbon here, CH as they're enumerated here, but there's 1 carbon and 2 hydrogens connected to the next carbon in the other chain. And so the tiebreaker is right here. This carbon is heavier than H. And so the priority 2 group is that entire sort of left-hand group in the structure. So 2 here and 3 here. And we keep sort of moving outward along the carbon chains until we reach that first point of difference. And again, wherever the heavier atom is, that's associated with the higher priority group. Double and triple bonds. How do we deal with these? We actually think of a double or a triple bond as 2 copies of that atom. So for example, a CO double bond is generally going to get higher priority than a CO single bond. Something like a carbonyl group is going to get higher priority than an alcohol group at the same position in another one of the chains connected to the stereocenter. And so, for example, in double and triple counting, double and triple bonds, if we were to list the atoms connected to this carbon highlighted in green, it would be 2 oxygens and a hydrogen. We count that doubly bonded oxygen twice. For a triple bond, we count the triple bond as 3 copies of the attached atom. So here, for instance, we have 3 carbons, quote unquote, attached. We have 1 carbon for each of these bonds in the triple bond. And so here, for instance, the triple bond is going to get higher priority than this double bond generally, because down here at the end, we think of this as having 2 carbons and an H. attached to it. Really, we could argue that this is 3 carbons and an H, I suppose, although we kind of don't walk back along the chain. In any event, this is going to end up having the higher priority as a result of this difference right here. So the upshot here is, again, we're going to double count double bonds, triple count triple bonds, adding the atom involved in the double or triple bond 2 or 3 times respectively. In some cases, it can be a bit tricky to rotate that lowest priority group back into the plane, particularly when you're dealing with cyclic systems. This can get a little bit tricky. This slide shows a nice trick for avoiding visualizing these rotations, although I stand by what the first bullet point says, that visualizing the rotation is really the best way to think about moving the molecule around. These kinds of mental operations of moving molecules around are going to make you a better organic chemist. But in any event, here's a little trick that eliminates the need for rotation. If we switch the positions of 2 groups or exchange 2 groups twice, we'll end up with the same configuration we started with. This is kind of like reflecting through a mirror and then reflecting again to get back the original structure. And we can exchange different groups when we do this, and we'll still get back to the original configuration. So for example, what we can do here is exchange groups 4 and 3, and then exchange groups 1 and 2, and the resulting structure has the same configuration as the first structure we dealt with, but now has the lowest priority group in the back, and we avoided the need to actually think about flipping the molecule over or rotating the molecule. This works best and is most useful, I think, when that lowest priority group is in the plane of the screen or the page. This, when it's not on a wedge or dash, this can get a little bit tricky, potentially visually, and so this trick can work nicely. And the last thing I'll say is just a brief warning about you have to do this twice. You must exchange twice. If you only exchange once and leave it at this is actually the enantiomer of this structure. So that's going to lead you to the wrong configurational label, the wrong configurational assignment. You'd assign here, for example, this looks S, but what you need to do is exchange again to get back to the original configuration. And in fact, the actual configuration in this original structure is R, not S. So be careful with that. So to summarize, the RS convention, or Cahn-Ingold-Prelog convention, first, we're going to identify those 4 atoms attached to the stereocenter. We're going to assign them priorities based on atomic number and deal with ties by going out along the chains of the groups until we hit the first point of difference. And then we're going to rotate the molecule into that standard orientation with the lowest priority group in the back and look at the sense of rotation from the highest priority group to priority group 3, from 1 to 2 to 3. That sense of rotation is clockwise. From our standard viewpoint, we're looking at an R stereocenter. I guess from your viewpoint, that would look like this. And if the sense of rotation is counterclockwise from our standard viewpoint, the configuration would be S. Let's practice with the RS convention by assigning configurational labels to the tetrahedral stereocenters in ephedrine, whose molecular structure is right here. This compound has 2 tetrahedral stereocenters, one here and one here, and each of these is associated with an RS label. So let's start with this stereocenter on the left. And let's start by prioritizing the groups. Now, the first thing you want to look for here is differences in atom type, differences in atomic mass or atomic number of the atoms directly connected to the stereogenic carbon. We've got an O, a C, and an H. And so pretty clearly, the O gets top priority. That's the heaviest atom here, and the H gets lowest priority. That is the lightest, and conveniently, for our standard orientation in a bit, it's already in the back. Now, what about these 2 carbons? Well, because they're both carbons and we've got a tie, we've got to consider the atoms that are connected to those carbons. The left-hand carbon, I've got 1, 2, and 3, double counting the double bonds, carbons linked to this one. Over here, linked to this carbon, I have a carbon, a hydrogen, and a nitrogen. So the first point of difference here, looking at the heaviest atoms, is this nitrogen versus this carbon. And so the group on the right actually gets higher priority as a result of this nitrogen here. And the group on the left, with only, quote, 3 carbons, gets priority number 3. Now we make sure we're in the standard orientation with the lowest priority group in the back. In fact, we already are, so we don't need to think or worry about rotating this at all. And we see that the sense of rotation here from 1 to 2 to 3 is clockwise, and this makes that stereocenter R the R configuration at that stereocenter. All right, let's move to the other stereocenter, which is the carbon linked directly to nitrogen. Now here, in terms of prioritization, again, we've got an H and a nitrogen, and these are pretty clearly the lowest and highest priorities, respectively. And to determine the 2 and 3 priorities here, well, we have a carbon linked to O and H and C. And here we have a methyl group, and so with 3 H's attached, right? So the first point of difference we would say is this O versus one of the H's linked to this carbon, and so the methyl group is going to get priority number 3, and this hydroxyl-bearing carbon is going to get priority number 2. And the sense of rotation here, 1 to 2 to 3, noticing that we've already got that lowest priority group in the back, points us to an S configuration right here. So RS ephedrine would be one way to talk about the name of this compound, and this shows us how we use prioritization and thinking about that standard orientation to assign RS labels. Now, this one was pretty straightforward because the lowest priority groups were already in the back. In general, you'll have to think about rotating the molecule or changing your viewpoint to assign RNS such that the lowest priority group, which is often but not always a hydrogen, is in the back.